In the second part of this lecture, we'll look at some more applications of the Nernst equation. In fact, we're going to look at how one might build a device that measures pH using a redox reaction and the Nernst equation. Now we can use the voltage generated by a redox reaction along with the Nernst equation to measure the concentration of a reactant or a product. For example, we just finished examining the following redox reaction, where dichromate, in the presence of acid, oxidized iodide to iodine, resulting in the reduction of dichromate to chromium 3+, and water is also produced. Now, since the standard potential, as we found out, for this reaction is 0.79 volts, and the number of electrons transferred in the reaction is written N as 6, the Nernst equation for this redox reaction could be written like this. Well, let's suppose we find a way to keep the concentrations of the chromium 3+ ion, the dichromate ion, and the iodide ion at 1 molar, but we allow the concentration of the hydrogen ion to vary. Now, if we rewrite the Nernst equation under these conditions, it would now look like this: 0.79 volts, which is the standard potential, minus 0.009867 volts, which is just the 0.0592 divided by 6, times the log of 1 squared, because we said we'd keep the concentration of chromium 3+ at 1 molar, over 1, the concentration of dichromate that we said we'd keep at 1 molar, times a hydrogen ion concentration to that 14th power, which looks a little intimidating, and then 1 to the 6th power when we said we'd keep the iodide concentration at 1. If we simplify this, since we have these factors of 1 in the numerator and some ones in the denominator, we can simplify this to saying that the potential, the measured potential, would simply be 0.79 volts times 0.009867 volts times the log of 1 over the 14th power of the hydrogen ion concentration. In other words, there's a direct relationship between the measured potential and the hydrogen ion concentration. And if you recall, pH equals minus the log of the hydrogen ion concentration. So rearranging the above equation that's in the yellow box further, we could say that the log of 1 over the hydrogen ion concentration to the 14th power is really the same thing as the log of the hydrogen ion concentration to the minus 14th power, exactly the same. And remembering the properties of logarithms, this power to the minus 14 can be brought out front of the log term, so I just did that there. And I'm going to take the focus off the 14 as having the minus charge by just inserting a -1 here. So this equation right here is exactly the same as this equation here. Just instead of -14, I'm writing 14 times a -1. Well, of course, the reason I'm doing that is because minus the log of the hydrogen ion concentration is the pH. So if we substitute that into the equation and we go ahead and multiply 14 times 0.009867, our equation simplifies to the measured potential equals 0.79 volts minus 0.138 times the pH. Now this is looking a lot like a straight line, and we can rearrange this equation so it looks exactly like a straight line equation. E equals minus 0.138 times the pH plus 0.79. So E here would be the value of Y, and pH the value of X. The slope would be minus 0.138, and the y-intercept would be 0.79. So now we have a direct relationship between the measured potential of this reaction and the pH of the solution in which this reaction is taking place. We can actually take this potential of this reaction and we can graph it as a function of pH using the equation we just derived on the previous page. And of course, you see we have a straight line relationship between the potential of this reaction, which we could measure with a voltmeter, as a function of pH. And on the chart here, of course, I've shown the values that I've used. So if the hydrogen ion concentration, say, is 0.01, the pH would be 2, and the measured voltage E would be 0.51, and you can see that on the graph right here. Now, if you were clever and knew how to write some code, you could write a piece of software on a computer chip that automatically converts the voltage that is being read by the voltmeter to a pH reading using this line as a calibration line, and you could get a pH reading for any acidic or basic solution. Now, here I bring up this little graphic and ask, does it bother you that the voltmeter reads positive and then negative values? In other words, that the potential is positive and then goes negative. Well, it shouldn't. Remember, a positive E means the reaction is spontaneous in the forward direction. If the measured potential is negative, then this reaction is just spontaneous in the reverse direction. This particular redox reaction would actually not be an ideal choice for use in constructing a pH meter. The fact that the dichromate ion is a cancer suspect agent might be one of the first reasons why you wouldn't use this reaction. But the principle here is important, and that is you're using a known redox reaction and the Nernst equation to actually monitor the concentration of one of the reagents in the redox reaction by monitoring the potential of the overall reaction as the concentration of the reagent you're monitoring changes. So if we can't use dichromate in a reaction like this to measure pH, at least in a practical way, how is hydrogen ion concentration measured in a real pH meter? Well, before we can answer that question, we need to discuss something called concentration cells. So let's take a look at that. A difference of potential, or in other words, a voltage, can be generated simply by a concentration difference across a semi-permeable membrane. Now, such a setup is called a concentration cell. Well, what I just put up here was a rather complicated looking diagram. We're going to work through this step by step, but this is an example of a concentration cell. So this figure is an example of a way we could, in the lab, set up a concentration cell. The beaker on the left-hand side contains a solid silver electrode immersed in a solution that's 0.1 molar in silver nitrate. So the solution this is in here is 0.1 molar in silver ions and 0.1 molar in nitrate ions. Now the beaker on the right also contains a solid silver electrode, and it's immersed in a solution of silver nitrate, only in this case the silver nitrate has a different concentration. It's 1 molar instead of 10th molar. So there's a difference in concentration in these two beakers on either side of this semi-permeable membrane, or the porous glass fritted disc there. So it's 1 molar silver ion and 1 molar nitrate on the right, only 10th molar silver ion and 10th molar nitrate on the left. Now the figure is giving us information about electron flow. And you say, well, sure, you've got electrons drawn here and they seem to be flowing from left to right. Excellent point. However, there's something else that gives us a clue. One of them is that it appears that the silver electrode on the left seems to be disappearing with time. You can see that it seems to be corroding, where the silver electrode on the right seems to be a little fatter underneath the surface of the solution because it seems to be growing with time. There seems to be silver building up here. And the reaction that's going on here, or the electron flow, is spontaneous because the voltmeter, which is reading a voltage, it's a positive voltage. So there seems to be a driving force for electrons to flow from the left beaker to the right beaker, even though both electrodes are made out of the same metal. Both solutions are made out of the same ionic compound, silver nitrate, but the difference is the concentration of silver nitrate is different in both beakers. So now you can start to realize why we're calling this a concentration cell, that there's a difference in concentration of the silver nitrate in both these beakers, and that seems to be what's driving the electrons from the left beaker to the right beaker. So the left beaker is where oxidation is occurring. Electrons are leaving, and that silver metal from the electrode is being turned into silver ion, and that electron's going across through the voltmeter and down into the electrode on the right. So we write the oxidation reaction on the left. This would be the anode on the left. And we put a 0.1 molar under the silver ion concentration here because we realize that it would change over time as the reaction proceeds, but starting out it's at 10th molar. Now on the other side we have reduction occurring, so this is the cathode, and on the other side the electrons would come over into the silver electrode, and silver ions from the solution would be reduced to silver metal and build up on the electrode. So we have a reduction occurring here, and the concentration of the silver ion on the right hand side in this beaker is 1 molar. Okay, now if we try to write an overall reaction for this, it's going to look rather strange because both half cells represent the same redox reaction. It's just that it's reversed in one beaker relative to the other, but let's give it a try here. The oxidation half reaction, as we wrote underneath the beaker on the left, is silver metal going to silver ion plus 1 electron, with the silver ion at 0.1 molar concentration. The reduction half reaction is silver ion at 1 molar concentration interacting or being reduced by 1 electron from the anode to form silver metal. And so if we wrote an overall reaction here, the 1 electron would cancel out, the silver metal would cancel out, and what would be left here is this strange looking overall redox reaction, which doesn't really look like a redox reaction, where we have silver ion at 1 molar concentration for the reactant, and silver ion at 0.1 molar concentration being the product. So the driving force in this concentration cell is simply the silver ion attempting to reach the same equilibrium concentration in each half of the cell. Now the Nernst equation can calculate the expected potential generated by this concentration difference. Well, how would it do that? Well, here's the Nernst equation. The standard potential, E0, would be 0, because if the silver ion concentration were 1 molar in both beakers, that would be standard conditions. There would be no potential generated. N is 1 because both oxidation of silver metal and reduction of silver ion involve 1 electron. And the reaction quotient here would simply be the product concentration, which we said is silver ion at 0.1 molar, over the reactant concentration, which we said is silver ion at 1 molar. In other words, 0.1 divided by 1, or 0.1, so that would be Q. So let's put in the numbers. E equals 0 volts minus 0.0592 volts over 1 times log of 0.1 turns out to be 0.0592 volts, or 59.2 millivolts. So what we see here is that a small but measurable voltage was generated by a concentration difference on either side of a semi-permeable porous disk. Now about that pH meter. A typical pH meter used in a general chemistry lab consists of a single glass electrode that you dip in the solution of interest. Now these types of electrodes have a fragile glass bulb at the bottom. As you can see in this diagram, there's a glass bulb here. It turns out that the glass thickness around this bulb is pretty thin, so oftentimes that bulb will be protected by a plastic cage, and your lab TA or your lab instructor will admonish you to be very careful with this electrode because it's very fragile. Okay, this pH electrode, which looks fairly complicated, works on some of the same principles as the crude concentration cell on the previous slide, but there's some important differences, so we'll try to point these out. Now, as in a concentration cell, there are 2 basically identical half cells, each one being a silver wire coated with silver chloride and sitting in an electrolyte consisting of chloride ions. Now in this diagram, one electrode is labeled in red, and it's called the inner reference electrode, and the other electrode labeled in black is the outer reference electrode. So you'll notice this red is a red wire, and then down here you have silver coated with silver chloride, and silver chloride is white. Of course, silver is not red, but we're differentiating this silver from the silver of the outer reference electrode, which we've colored black here, but at the tip of this black wire, it is also coated with white silver chloride. So you have 2 reference electrodes, an inner and an outer. So you basically have 2 identical half cells packed in this glass tube. Now, as in a concentration cell, the redox reactions at the inner and outer electrode are identical, but they're reversed relative to one another. Now, which electrode undergoes oxidation and which reduction depends on the concentration of hydrogen ion in the solution whose pH you're measuring. In the oxidative direction, silver metal would react with chloride, and an electron would be removed from the silver metal. You'd end up forming silver chloride, and that electron that's removed is right here. In the reductive direction, silver chloride would be reduced back down to silver metal and a chloride ion. Now, unlike a concentration cell that we showed on the previous slide, the ion of interest, which is hydrogen ion here, does not appear in the redox reaction associated with the electrodes. Rather, the specially formulated thin glass membrane develops a small potential difference between the inside of the bulb, which contains 0.1 molar hydrogen ions, and the outside of the bulb containing a solution of a known concentration of hydrogen ions. The inner and outer reference electrodes monitor the potential difference that's built up by the concentration difference between the inner part of that glass bulb and the solution whose pH you're trying to measure. Now, in reality, a pH electrode is a special type of concentration cell called an ion selective electrode, and the glass membrane in the pH electrode is formulated to selectively measure hydrogen ions. Now, in case you're interested, the measured potential E is a function of pH in this pH electrode according to the following equation. E equals a constant times another constant beta times 0.0592 times the pH. And you determine the constant and the value of beta when you calibrate the pH electrode with 2 buffer solutions in the lab. Let's talk a little bit about ion selective membranes in nature. Pacemaker cells in the human heart each have a cell membrane that can act as an ion selective electrode with respect to its ability to control the flow of ions through the membrane. Potassium ions in particular, but also sodium ions and calcium ions. So here's a rough cartoon where we attempt to draw a pacemaker cell, and we have the cell, we have an ion selective membrane around the cell, and we have what's outside the cell. Inside the cell, we have what we would call intracellular fluid, and outside the cell, extracellular fluid. The intracellular fluid inside the cell has a concentration of potassium ions of around 0.135 molar. The concentration of potassium ions in the extracellular cellular fluid much less, 0.004 molar. Now the difference in potassium ion concentration between the inside of the cell and the outside of the cell across that membrane sets up a concentration cell. And you would probably not be surprised to find out that this cartoon is a little oversimplified because there are other ions involved besides potassium, but we're going to zero in on only the potassium ion concentration differences in the intracellular fluid versus the extracellular fluid, just to make a point here. Let's write a redox equation showing the change in potassium ion concentration when going from the inside of the cell to the outside of the cell. And this shouldn't look too goofy at this point because we actually wrote a very similar equation to this when we talked about our silver ion concentration cell back in a previous slide. Now, since we're operating in reality at body temperature, 37 degrees C, rather than 25, we'll use the long form of the Nernst equation. We won't assume the temperature is 298 K to calculate the potential difference E across this membrane. So what we'd have here is the long form of the Nernst equation, and I've put in the expression for Q here, which would be, as we've written our reaction, the concentration of the potassium ion in the extracellular fluid divided by the concentration of the potassium ion in the intracellular fluid. The standard potential here would be 0 volts, because if both of these were at 1 molar concentration, there'd be no potential. N is 1, since we're dealing with the potassium ion. And we have the value of R, Faraday's constant, a temperature of 310 K. If we put all these values into the Nernst equation, it looks rather formidable, but it is not. We have 0 volts minus 0.0615 volts, which is the result of taking 2.303 times the gas constant times 310 K divided by 1 for N times Faraday's constant. And then we'd have the log of Q. Q is 0.004 over 0.135. Remember, those are the concentrations in the extracellular and intracellular fluid. And the log of that term turns out to be minus 1.528, which we'd multiply by this other factor, and we'd subtract, this would turn out to go positive because you'd have a negative times a negative. So the potential from the concentration difference across this membrane is 0.094 volts or 94 millivolts. So this has generated a real potential, and this is generated by the difference in potassium ion concentration across a cell membrane. Now, pacemaker cells in the heart, through changing concentration gradients of ions such as potassium, sodium, and calcium, can generate systematic voltage changes. So we calculated a voltage for one concentration difference, but if the pacemaker cell finds a way to make the concentration differences across that membrane change in a rhythmic pattern, then the voltage will change in a rhythmic pattern, and you'll see the electrical potential change with time in a very periodic way. And if the pacemaker cells in your heart are doing this, these voltage changes can be monitored by sensors on your skin during an EKG. So you can see that pacemaker cells can set up concentration cells in which voltages are generated, which we can monitor or at least model with the Nernst equation, so that these pacemaker cells can produce a rhythmic and periodic change in voltage, which can be monitored, and this voltage is what's keeping you alive.